Hello students, welcome to this lecture, fourth lecture on elements of discrete mathematics. In this lecture, basically we are going to discuss the supremum and infimum of a set and supremum and infimum of a partially ordered set. Why we are discussing these concepts in discrete mathematics? Because in discrete mathematics we are going to discuss the next topic is the lattice. In order to define a lattice, you must know the concept of supremum and infimum. So, in this topic, supremum and infimum of a set, the first definition is a set bounded above. When do we say that a set is bounded above? So, definition is here. Let S is a non-empty subset of real numbers. R is the set of real numbers. S is said to be bounded above if there exists a real number u, real number u such that x is less than equal to u for all x belongs to S. And here S is called the upper bound for the set S. In fact, we have to find a real number from which all the elements of this set S are either smaller or one of the element may be equal to that. So if we are able to find such a real number, then this real number u will be called an upper bound for the set S. For example, here we have one case, the set of all negative integers. If we have set of all negative integers, then in this set we are going to have -1, -2, -3, -4, etc. Now if we put these integers on a line, we have 0, -1, -2, -3, etc. As far as we go on left hand side, the value of integer is smaller, and as we go on the right hand side, the value of integer is larger. So you can see, can we find a real number from which all these elements of this set of negative integers are smaller or maybe equal? So yes, here we can talk about one number, that is 0 is upper bound for the set. Why? Because all elements x belonging to set z negative, we can say x is less than equal to 0. So we can say that 0 is an upper bound. 0 is an upper bound for this set of negative integers. Again, we talk about this set. This is the closed interval 1 to 3. In this set, we will be having all the real numbers which ranges from 1 to 3. So in fact, this set also has infinite number of elements. Now, can we find a real number from which all elements of this set or all numbers in this set are smaller or maybe equal? So of course, we can say that in this case we can consider u equal to 3, maybe 3.1, 3.2, etc, etc. So we can say, particularly suppose we take u equal to 3, then we can say x less than equal to 3 for all x belongs to this interval 1 to 3. So here we can say 3 is upper bound for this set and this set is bounded above. Now question arises, whether for a given set there is only one upper bound or there can be more than one upper bound. So here one note is given. If S is the bounded above set and U is the upper bound for the set S, then every real number greater than U is upper bound for the set. Thus we can say if a set is bounded above, there can be a class of upper bounds, or you can say for a given set there can be infinite number of upper bounds. For example, for this case, not only 0 but every number which will be on this side, every number which will be on right side to this -1 will be the upper bound for this set. Even -1 is also upper bound for this set. You can also take For this case, you can also take u equal to -1. Then u equal to -1 will also be upper bound for this set, because for all x belongs to this z negative, this x is less than equal to -1. So we can say -1 is also upper bound, and all the numbers on right hand side of this line from -1 onward will be the upper bound for this set of negative integers. So we can say for a given set there can be infinite number of upper bounds if it is bounded above. Similarly, for this case, every number from here 3 onward, every number can be the upper bound for this set. So infinite number of upper bound for this set also. Now the least upper bound. For least upper bound, we can talk here. For example, the same set I'm going to take, the z negative, the set of negative integers, -1, -2, -3, etc. So as I explained with the help of this line, that is 0, -1, -2, -3, etc. All numbers on this side will be upper bounds, upper bounds. And among these, there is 1, -1. Among these, this is the least number. Among all upper bounds, which one is the least? That is -1. So u equal to -1 is least upper bound for the set z negative. For example, if we are taking this set, the closed interval 1, 2, 3 already given on the last slide. So here I told you the representation is like that, 1, 3. So in this case, every number on this side is the upper bound for this set. So we can say among these, which one is the least? So 3 is the least. So this is the least upper bound. So I can say u equal to this 3 is least upper bound for this set, for the set this interval 1 to 3. Suppose we take a finite set. Suppose I'm talking about here 1, 2, 3, 4. This is the finite set. In this case, all numbers greater than or equal to 4 are upper bounds. So here the least upper bound of this set S is 4. So in general, the definition of least upper bound can be given like this: if the set of all upper bounds of set S, which is bounded above, has the smallest member, say W, then W is called the least upper bound. For example, here I told you that all numbers on right hand side of -1 will be the upper bounds, and among these the least one is -1. So -1 is the least upper bound, and this least upper bound is also called the supremum of the set S, and sometimes in short we denote it by supremum S, supremum of S. Other way we can also define, if W is the least upper bound for a set S, if number one, W is upper bound, the first requirement is that it should be the upper bound, and second requirement is that if W dash is any other upper bound for S, then W must be less than equal to W dash. Means this W must be smallest among all the upper bounds. Here you are taking that W is any other upper bound. Therefore, the condition is that the least upper bound should be smallest among all the upper bounds. For example, here in this case, we have taken that W equal to 4 for this case, and there can be many W dash. W dash can be 4.1, 4.2, 5, 6, 7, etc. So why this is least upper bound? Because this W is less than equal to W dash. W dash is any other upper bound. So that is why we are calling this W is least upper bound for this set. So we can define least upper bound of a set either in this way or in this way. So this is the definition of least upper bound of a set or supremum of a set. So these are the two notations here. Next is the set bounded below. Exactly in the same manner as the case of least set bounded above, we can talk about a set which is bounded below. If S is the non-empty subset of real numbers, and if there is an element V belongs to R such that all elements, all X belonging to S, all elements are greater than this particular element V, then this V is called lower bound for the set S. This is called the lower bound for set S, and set is called the bounded below set. The one example here, if we are considering a set of positive integers, Z positive in fact, we will have 1, 2, 3, 4, etc. So if we represent these on a line, we can say this is 0, 1, 2, 3, 4, etc. So every number on left hand side of this one will be the lower bound. Means all elements of this set Z positive are greater than any number if that is lying either at this point or on the left hand side of this. So particularly we can say 0, if we consider this, 0 is the lower bound. 0 is the lower bound for this set. Similarly, any number here I can say 0.5, 0.5, 0.6, etc. all will be the lower bound for this set. Now here for this case you can easily guess that if we are representing it like this 1, 2, 3, and any real number which is on left hand side of this and starting from 1 will be the lower bound, for this set. So among these, the 1 is lower bound. I can write here 0 is the lower bound, 0.5 is lower bound, etc., etc. So it can also have many lower bounds. So exactly in the same manner as the case of upper bounds, a given set can have infinite number of lower bounds. Now all the lower bounds, among all the lower bounds, there is greatest one. For example, here many lower bounds are there, but among them one is greatest. One is the greatest, and we are calling it, let in this case v equal to 1. So 1 is the greatest lower bound for this set, and particularly in this case 1 is also the greatest lower bound or infimum of the set 1 to 3. So this is the definition of greatest lower bound, and sometimes we also call it as infimum of the set or the greatest lower bound. It can also be represented by GLB, and supremum or the least upper bound is also represented as LUB or supremum of the set. This is the notation, and this is greatest lower bound GLB, or we also represent it by infimum of the set. So exactly as the case of least upper bound, the greatest definition of greatest lower bound can be given in this manner and in this manner. In the two cases, the set of positive integers and another set is this 1, 2, 3, I can say the greatest lower bound of this Z positive set is 1, and the greatest lower bound of this set S, this one, is 1. Suppose I am talking about this set, let 2, 3, 4, 5, 6, this is any finite set. So for this I can say the greatest lower bound of let this set is S1, S1 is equal to 2. So that is how we can define the least upper bound and greatest lower bound of a set bounded above and set bounded below. Now we can also define here a bounded set. What is a bounded set? A set is said to be bounded if it is bounded below as well as bounded above. Bounded below as well as bounded above. For example, this case, this set this is bounded below because the greatest lower bound is 1, and bounded above because least upper bound is 3. Similarly, Now if we talk about this set of positive integers, this set has elements 1, 1, 2, 3, etc. It has least element but not the greatest element. It can go up to infinity. So this is bounded below but not bounded above. Similarly, if we were talking about set of negative integers, in that case you can see 1, 2, -1, -3, etc. etc. It has the smallest element, sorry, it has the greatest element but not the least element. Therefore, this is bounded above but not bounded below. So a set can be either bounded below but not bounded above. A set can be bounded above but may not be bounded below. And if a set is bounded below as well as bounded above, then that set is called a bounded set. Before moving further, let us discuss the definition of least common multiple and greatest common divisor of two integers. First, we define the GCD, the greatest common divisor of two integers. The greatest common divisor of two integers a and b, two integers a and b, is the greatest integer that divides both a and b. Greatest integer that divides both a and b. Other way we can say, if we say that d is GCD of two integers a and b, then what happens? Two things happens. Number one, d divides a and d divides b. Second thing happens, that if there exists some d dash another integers such that divides a and b both, then what will happen? Then this d dash will also divide d. Then we say that this d is the greatest common divisor. Why we are calling it as greatest common divisor? Because d is the divisor of a, d is the divisor of b, means d divides a completely, d divides b completely. And if there exists another divisor which is dividing both, sorry, d dash divides a and d dash divides b, in that situation this d dash also divides d. So of course, because d dash divides d, so d is the greatest. D is the greatest. It means d can be divided by any other divisor. That is why we are calling it as a greatest common divisor. So you can see in this example, if we have two integers a and b as 24, and that this thing is a and this is b, then 6 is the greatest common divisor. Why 6 is greatest common divisor? Because 6 divides 24 and 6 divides 24 and 6 divides 18. However, we can have another integer which divides both. For example, I can say this 3 divides 24 and 3 divides 18. 3 divides 24, 3 divides 18. So in fact, this thing is d dash, this thing is d dash in this case, and this thing is d, this thing is d. So you can observe that this d dash is dividing d. So because of that, we are saying that this d is the greatest common divisor. Another situation happens if we take d dash equal to 2, d dash equal to 2, then again this 2 divides 24, 2 divides 24, and 2 divides 18. So definitely again this 2 divides 6. That is what is happening, this d dash divides d. So we can say that here the greatest common divisor means, however 2 and 3, 2 is also common divisor because it is dividing both these integers 24 and 18. And 3 is also a common divisor because it divides 24 and it divides 18. But which one is the greatest? The 6 is the greatest common divisor, which is dividing both these 24 and 18. So 6 is the greatest common divisor. Similarly, we can talk about the least common multiple. Least common multiple of two integers, two positive integers, is the smallest positive integer that is multiple of both. Multiple of both. In this situation, how we define, like in this case, we will say that M is LCM of A and B. If what happens, number one, A divides M, and when we say A divides M, it means M is multiple of A. M is multiple of A. And similarly, we say B divides M. And if there exists M dash such that another situation is A divides M dash and B divides M dash, then what happens? Then M divides M dash. Only then you will say that M is least common multiple, because here we are talking about least, so any other multiple should be divided by M itself. For example, in this case 2 and 8, the LCM is 8. Why? Because in this situation A is 2 and B is 8, so I can say this 2 divides 8 and 8 divides 8. So we are taking that this is uh, in place of M, 8 is in place of M. Moreover, we can have 4 divides 8 and 8 in place of 8, sorry, we can have 16. 2 divides 16 and 8 divides 16. So in fact this is M dash, means we can have other multiples also. We can have 2 divides 32, 2 divides 32, 8 divides 32. So now M dash becomes 32. But it means 16 is common multiple of 2 and 8. 32 is also a common multiple of 2 and 8. And here 8 is common multiple of 2 and 8. So which one is the least? So least is 8. The least common multiple is 8. So that is why we are saying that LCM of 2 and 8 is 8. So this is concept of least common multiple of two positive integers. So now we are moving to the concept of supremum and infimum for a partially ordered set, which we call as POSET. Before moving to the supremum and infimum of partially ordered set, we must notice certain things here. The symbol less than equal to is essential to define a supremum and infimum. You can see in the earlier definitions when we were talking about supremum and infimum, here greater than equal to is there, or less than equal to is there. In this case, less than equal to is there. So in real numbers, the meaning of less than equal to or greater than equal to is something different. In real numbers, the meaning of this is less than equal to is in usual sense. That means if we are writing 2, this clearly this 2 is less than 3. This 2 is less than equal to 3, etc. So the meaning in the real numbers is this. But in a partially ordered set, the symbol means a relation. Symbol means a relation. And the meaning of relation can be different in different partially ordered sets. For example, you see, if we have this partial order set, let S is non-empty set, PS is the power set, PS is the power set of S. Then we already know that, we have already proved that it satisfies all the conditions of partially ordered set under the relation if A is less than equal to B if and only if A subset of B. Under this relation, we have already established that this PS forms a partially ordered set, and here the meaning of this is inclusion, means A includes B, or you can say A is subset of B. So in this situation, the meaning of less than equal to is inclusion. And with respect to this inclusion relation, we have established that it is a partially ordered set. Now you consider B equal to any subset of this. We are considering this B any subset of PS. We are taking any subset of PS. Obviously, when it is subset of PS, its elements are also set in itself, means A1 is a set, A2 is a set, A3 is a set, A4 is a set. Of course, A1, A2, A3, A4 belongs to PS. Now we take U as the union of all these four sets. Then union of all these four sets consists all the elements of sets A1, A2, A3 and A4. Then definitely A1 will be subset of U, A2 will be subset of U, A3 will be subset of U, and A4 will be subset of U. In particular, we can, in general, we can say that A is a subset of U for all A belongs to B. A belongs to B means if you take any element from this set B, then A is subset of U. When you say A is subset of U, then according to this definition of the relation here, we can say A is less than equal to U for all A belongs to B. Therefore, we can say in the uh, in the in view of the definition of upper bound of the set, U is, because all elements of B are less than equal to U, so U is an upper bound of B, and in fact it will be the least upper bound of B, least upper bound of B. Why? Because in this union, if we add more sets, so there can be infinite number of upper bound for this, but among those this U is least one, so that is why it is least upper bound or supremum of this set B. So this was one situation where this symbol less than or equal to was having some different meaning. Now let us look at the another form of this. When we take the intersection, then L will becomes the lower bound of B, and this is greatest lower bound or infimum of set B. Now we look at the another situation. For example, we take this the set of all divisors of 12, D12, we are representing it here, and here we take the relation divisibility. This vertical line is the divisibility relation. So here meaning of less than equal to is divisibility, or we can say A is less than equal to, we define the relation as A is less than equal to B if and only if A divides B. Then with respect to this relation, we have already established that this type of set D12 with respect to divisibility forms a partially ordered set, is a partially ordered set. Now let us look at it. Now to find the upper bound of D12, we have to look for a number U such that A is less than equal to U for all A belongs to D12. And in this situation, the meaning of less than equal to is divisibility, means we have to look for a number U such that A divides U for all A belongs to D12. Means we want to find a number which is divisible by every element of D12. So there can be many numbers which can be divided by every element of set D12. In fact, D12 has divisors of all divisors of 12, 1, 2, 3, 4, 6 and 12. So we can have 24 in place of this. Then 24 can be divided by every element of this set, every number of this set. We can have 12, we can write here 36, we can write 48, etc., etc. So in fact, we can say that here A divides 24, 12, 36 and other numbers of this form. When we can say like this, and divisibility means less than equal to, so we can say A is less than equal to 24 even with 12, 36 and 48, etc. So we can say this, that 24, 12, 36, 48, etc. all are the upper bounds of D12. Now which one is the least among them? We can see among them least is 12. So we can say least upper bound or supremum of D12 is 12. Least upper bound or supremum is D12. And you can also say this 12 is LCM of all these numbers. LCM of all these numbers, least common multiple of all these numbers. So I can say in this kind of set, in this kind of partially ordered set, the meaning of supremum of two numbers, the meaning of supremum of two numbers A and B, supremum of two numbers A and B means LCM of two numbers A and B. Now for the lower bound, the case reverses. We have to look for a number such that L is less than equal to A for all A belongs to D12. L, that means L divides A. We have to look for a number such that L divides A for all A belongs to D12. So such a number is 1. such number is 1 by which all these elements can be divided. So GLB, the greatest lower bound of D12, or you can say infimum of D12 is 1. And in fact this one is the GCD, greatest common divisor of all these. So in this kind of set, if we want to talk about infimum of uh, two numbers, then it means it will be GCD of two numbers A and B. GCD of two numbers A and B. Similarly, in case of this kind of set, when n is the set of natural number and this is the less than equal to sign is usual sense. In that set, least upper bound of AB will be maximum of these two numbers. For example, I say least upper bound of two numbers 1, 2 is equal to maximum of 1 and 2. Means we have to select the maximum number out of these two, and maximum is 2. And if I talk about greatest lower bound of these two numbers, then that will be minimum of 1 and 2, and definitely that is 1. So this greatest lower bound is 1. Now on the basis of these concepts you can work out this exercise and try to do every question, and it will be very fruitful. Thank you.